Hi, everyone. Thanks for joining us for today's C2 Smart Distinguished Speaker webinar. I'm John Patinos, a project manager here at C2 Smart. As always, this webinar is going to be recorded and uploaded to the C2 Smart YouTube channel with all of our other webinars and recorded seminars. If you have any questions for our distinguished speaker today, you can use the Q&A button at the bottom of the screen, and we're going to answer your questions live at the end of this webinar. Today's distinguished speaker is Professor Yinhai Wang, Professor of Transportation Engineering at the Department of Civil and Environmental Engineering, and an adjunct professor in the Department of Electrical and Computer Engineering at the University of Washington. He's also the founding director of the UW Smart Transportation Applications and Research Laboratory, that's STAR Lab, and is the director of the Pacific Northwest Transportation Consortium, PACTRANS, which is the Region 10 USDOT University Transportation Center, where he's been director since 2012. And he's also a C2 Smart PI with a project on roadside sensors and edge AI for driving assistance. Before you begin, Professor Wang, I can quickly turn it over to C2 Smart Director, Professor Khan Osby, to say a few words.
Thank you, John. And thank you for this great opportunity to have Professor Yinhai Wang. So last year around this time, a little bit earlier, I was in Seattle, and we were expecting Yinhai to come here in person and enjoy New York City. We talked about it. Unfortunately, we had the COVID situation. So now it's really not a replacement, but just for the time being, we are really glad to have him, and we are looking forward to a very interesting talk. But we want to have like a blank check from him that he will show up in person when this thing ends and COVID. The vaccine comes out. We want to have him as our guest here, as our honored guest, and then enjoy New York, and also show him our new center facilities, which is built for C2 Smart, and we didn't have a chance to get in yet. So probably he'll be our first guest at that time. With that, I'm just gonna ask him to give us a great talk, and we'll listen to him, and then please feel free to ask questions, and then hopefully there'll be some discussion time at the end of his presentation. So thank you, Yinhai.
Thank you, Ken, for your kind invitation. I really look forward to visit your university. And also thanks, John, for your introducing me to the audience of C2 Smart. Good afternoon, everyone. It's my great pleasure to be here presenting our research work at the University of Washington STAR Lab. So the presentation topic today is edge computing for safer and smarter transportation applications. In this talk, I'm going to introduce the edge computing work that we have been doing, and also using several projects as examples to show how this technology could be applied. First of all, maybe not everyone have ever heard about the University of Washington Smart Transportation Applications and the Research Lab. This is the laboratory at the University of Washington try to support research and also education. We actually have a lot of very interesting active research projects ongoing. We collaborate with multiple agencies and companies to address the challenges in smart transportation. If you're interested to know more, you can visit our website. It's very easy to remember, www.uwstarlab.org. You're also welcome to join us visiting, or if you're interested in graduate study, you could also consider joining us. So we're facing a lot of transportation challenges. If you talk about traffic, people say, oh yeah, traffic jam, that's horrible. It's almost everywhere in the big cities. If you look at the reason on why we have such a big traffic congestion problem, you can look at actually the chart at the right side from 1980 to 2018. So basically our roadway mileage increased about 10%. At the same time, you see the top line, which is vehicle miles of travel, that increased over 106%. So you see the gaps getting bigger, and this difference is not simply due to the increase of the vehicle population. You can see this red line is representing the increase of vehicle population. So we can tell that while the vehicle population increases, we also see increase of driving distance for each vehicle. So this is the challenge we're facing. We don't have enough money to build enough new roads to address the capacity challenge. So we need to be smarter and figure out how we can use technology to address the traffic congestion problem. Another big challenge, actually we talk almost every day on our news media, is the traffic safety challenge. In the United States, you see we still have over 66,000 people killed each year. In the recent years, we also see a strong increase in pedestrian kills. So these are all the issues that cause a lot of damage to our society and the economy. So as transportation professionals, we need to consider how we can address the challenge. In the recent decades, connected vehicle technologies are getting popular. And US DOT websites also show that this technology will be promising in addressing the challenges that we're facing. It will reduce traffic delay by 33%. It will eliminate or mitigate the severity of up to 80% of the non-impaired crashes. It will also have a lot of benefits to the environment. For example, yield fuel savings of up to 22%. Maybe you all heard about connected vehicle technologies. This is basically making roadway users, such as cars, pedestrians, they are connected to the infrastructure and also connected to each other. So if you look at this particular slide, we see vehicles connect to each other, and they also connect the infrastructure through the roadside unit. And then in the infrastructure side, there will be a lot of data processing and decision work. And then recommendations or warning signals will be passing back through the roadside unit to the roadway users. So this is a terrific system. So we really have a lot of hope that this particular system is going to help improve efficiency and also reduce the crashes. However, this system is powerful, but it's kind of too complicated in my opinion. If you look at this particular slide, we see cars connect to the infrastructure system through onboard unit, sending signal to roadside unit. And then the roadside unit will be passing the signal to the traffic control center or the control device. At the same time, the traffic sensors collecting traffic condition information feed the traffic control device and the traffic control center. And the control center on the device will be making decision. For example, adjust the signal timing plan, etc. And then such information will also be going back through the roadside unit and finally delivered to the connected users. At this point, they're pretty much connected vehicles. Several days ago, actually, FCC voted basically to terminate DSRC. So we're going to switch to CV2X. The new protocol is still under development. Once that one is done, I think we're also likely to be communicating with roadway users like pedestrian and bicyclist directly. But the DSRC needs an actual device and make it hard to connect from the roadside directly to the users with cell phone. So we can see actually in this particular slide, the sensor devices does not directly work with this connected, like a roadside unit. And the makers of these devices are also not optimizing the design or the functions to support this application. I think this may be the reason on why connected vehicle, the concept has been there for over several decades, but we see almost very few success stories talking about this. There are also devices like the roadside units installed. It doesn't seem to be used as expected. So these are actually the problems we see in implementing this wonderful connected vehicles idea. To make the connected vehicle system work better, we need to have a good information to process and feed to the roadway users. You can see actually this picture shows a lot of sensors installed due to whatever purposes. The problem is each particular sensor will be collecting information, and the information will be feeding to their own data management system. And each data system actually cannot be interoperable. And so if you are the end user, you want to pull the information from each database system, integrate them, and make a good use is kind of challenging. And this is particularly challenging for transportation engineers who are not trained with substantial data management skills. So how do we address the challenge? Should we figure out a better way, to collect information and integrate it easily? So the current system not only have a lot of sensors, but these sensors are likely to be in different locations and collecting data at different resolution level. So this adds another level of difficulty when you try to integrate the data. So one more challenge is, if you want to monitor the roadway condition and give driver the right warning information, you need not only traffic volume information, you also need, for example, weather visibility. But these sensors are kind of rare on the existing roadway system. And if you want to install these devices, it's going to be expensive. So transportation agencies may not have the amount of money to really cover our roadway system with all the desired sensors. So one solution that we can see is make this whole thing easy. So if we have a kind of magic device here, this magic device can collect traffic information, weather information, and communicate with the road users, communicate with the traffic control center. I think the whole thing will become a lot easier. So this is basically showing the needs of integration of traffic sensing, decision-making, data fusion all together in one device. So the device that we developed and we're still continuously developing is the system called mobile unit for sensing traffic. So this is actually the research work we are doing. And in today's presentation, I'm going to show some details about this new technology and also encourage you to develop your applications based on this particular edge computing data platform. So what we have been doing at this point includes adding computer vision functions to this particular device. We can also detect media access control address, and that's actually the information people are using for estimating travel time. We have to do this on this device to avoid the challenge for a broad bandwidth communication needs. Nowadays, there are a lot of new computer algorithms in the artificial intelligence domain being developed, and they are quite powerful. So we also applied AI technology, but not on a server computing device. We're applying this technology on this edge device, on a master sensor. So we have to figure out how to do it as an edge computing. And this is actually a challenging task. And we're glad we have made some progress. and we'll share some of our success stories with you today. So once we have all those functions integrated in this magic device, we kind of integrated data collection, data fusion together in this device. And we could send the data to the database system and supporting the decision-making at the traffic control center. We can also make simple decisions on the edge side. For example, if you detect black eyes on this area, you could just send out the signal to the message to the users. So this is a dangerous road segment with the eyes. And such a decision could be relatively easy. So the device could communicate, with the local decision and the center decision, communicate with the users through like a edge device, like cell phones, user like an iPad, etc. You can also directly feed the signal control, or like a advanced traveler information system. It can also directly control other devices on the road. So the right side photo shows example installation of this particular device. So today our main focus is about edge computing. Maybe you wonder, what is edge computing? So edge computing is basically try to process data at the edge device. So you see like we have a lot of sensors deployed, particularly after the Internet of Things gets popular. Different places have various kinds of sensors, and some of these sensors carry certain computing capability. And you can consider these devices as the edge device. If it processes the data locally, it can avoid sending a lot of data to the server. And so this is going to cost more for communication and require higher bandwidth to handle the communication needs. So in edge computing, data is processed by the IoT device itself or by a local computing device, rather than transmitting everything to the server or to the cloud. So the idea is basically manage and process the data as much as possible on the edge end, avoid overloading the server and the communication system. So why we need to do edge computing? This is a solution to address the increasing demand for computing service to process and store big data. You can imagine if we have a lot of sensors deployed, and these sensors all monitoring or collecting data for a specific purpose. If all these data must be sent back to the server, you can imagine the communication system will be overloaded or very busy. And at the same time, the server side will be difficult because you cannot transfer everything to the server, and the server will have to process the data based on limited context information. So this is all not as good as you leave the processing work at the end, at the edge side. So edge computing will be efficient for data processing. So it has certainly major advantages: reduce the communication bandwidth, reduce the computation load at the centralized cloud server, reduce overall costs for sensors, computation, data transmission, maintenance, etc. It is also friendly to large-scale implementation, like our transportation system network. You have a lot of sensors. If the sensor collects data, particularly the video sensors, collecting video data and processed locally, send only the computed results back to the server for storage. That's going to be a lot more efficient than you imagine. Maybe thousands of cameras will be sending the live stream to the server. This will also have better privacy protection because it will not be storing the raw data and transferring the raw data on the server side. So if you get the valuable information out from the raw data, probably raw data can be directly discarded. So there are, of course, also challenge for edge computing because the edge devices are typically small with very limited computing power. Your algorithm has to be optimized. It must be a lightweight algorithm. And also, the edge may not be able to do everything on the edge side. In this case, you have to consider how do you distribute the tasks, the computing tasks and the load between the edge device and the server or the cloud. And you integrate the edge device and the server as one system. There are certainly challenges on the integration and the reliability side. So these are all the challenges we're facing. But I think there are solutions for each of them. And also with the quick advancement of computing technology, the computing power at the edge device is also increasing quickly. So a lot of video cameras installed in the urban area. So these video cameras could be great information source, and many transportation agencies are using the video input to process like a traffic data, including hotspot of conflicts, volume, vehicle type data, etc. We actually teamed up with the city of Bellevue and Microsoft at the very beginning, and later we worked with Traffic Soft and together for Safer Roads, process the video camera data at the city of Bellevue and try to get a better understanding about vehicle flow conflicts at different intersections, identify improvement directions for signal control and urban street management. But this work was done pretty much on the server side. So we get all the video cameras transferring the data to the server, and we process the data at the server. Clearly, this is going to be requiring fast speed communication. Ideally, the work will be done at the edge side, so we can use only the regular cell phone data communication package to handle the communication needs. Particularly, the real-time video analytics applications, normally for traffic management, we will need like a low latency. And because video data is information rich and huge in size, the communication bandwidth needs to be very broad. And to process the video, typically it requires high computing power. So we can see for the low latency and the large bandwidth, these two sides certainly make it desirable to do the video analytics at the edge device. But the high computing power is actually the challenge for the edge device. But if you do this on the server side, so these first two requirements are hard to satisfy. And some researchers at Microsoft, actually those are the group of people that we work together for the first phase of the Vision Zero project. So they consider real-time video analytics is the killer app for edge computing due to the challenges that we mentioned earlier. However, transportation just has huge needs for this kind of edge computing, and it takes actually the leading edge with smart technology, and this kind of information collection processing is a very important foundation for smart decision making. In transportation world, you see we have this connected vehicle application and the smart infrastructure initiative, etc. So these all make it highly desirable to do the edge computing, so we can process the information timely, more efficiently for a variety of applications, supports the infrastructure. So now I would like to show you several examples. And the first example I want to show you is edge computing for highway monitoring. This is actually the research work we're currently doing with the support from Norwegian Public Road Administration. So the challenge they're facing is they have a lot of fisheries in this area. Actually, this is inside the Arctic Circle. The fish they raised needs to be transported using this E8 corridor across the border with Finland to load the fish on airplane in the Helsinki airport and then fly over Russia and deliver to the Asian customers. So this corridor actually is a relatively old corridor. The design is not quite to the European standard. You see actually this picture shows the roadway is quite narrow. If you have two large trucks meet inside the tunnel, it's very hard for them. So there are actually side swipes, kind of accident happens very frequently. If we try to make these corridors travel more reliable, that means if there's any incident happened or any weather event from the truck freight vehicles, moving smoothly using this corridor, we could inform the traffic management agency so they can assign an incident response truck to this area and try to handle the incident. Because this is in a quite rural location, it's not affordable to assign, an incident response truck just to patrol in this area regularly. So such a system that we propose to them will be installing 9 mast sensors with the Ethernet internet connection along this corridor. So we can tape the roadway into 8 different segments. And we measure the travel time and measure the roadway surface condition so we can process the data to see if there's any problem with the roadway. If there is an incident occurred in any segment, we can let the traffic management team know so they could assign the incident response crew to the location to fix the problem. So the objective of this project is certainly try to make sure freight vehicles and the regular passenger vehicles will have higher travel reliability on this road. If there's any problem happened, fix the problem. So this will be involved in our detection for incidents, sending a warning message to traffic operation centers. We can also send a message directly to road users if they have a device to receive the information. We measure section travel time and calculate the reliability. We look at the reliability and the road surface condition. We know if the roadway surface is covered by snow or ice, certainly the travel time will be longer. If it's dry pavement, will be shorter. So we will collect data and see when the travel times are beyond the reliable range. And that is actually the moment we need to warn the traffic control center for their attention. So at this point, we have implemented different kind of functions into this device, including travel time data collection, communication capability, road surface monitoring and detection, traffic counting, and the vehicle classification, collecting temperature and humidity. I mentioned earlier, most of our roadway system do not have the temperature sensor or like a weather station. If we have such sensor that can detect temperature, humidity, and also visibility, we can somehow serve like a weather station. So this kind of information will be critical for our traffic operation center to make the right decisions under challenging weather conditions. So in this particular application, we try to get everything installed on the edge side. So we hope the detection work will be all done in the edge side. So we have actually the AI algorithm trigger you know, like if you run the AI algorithm to detect traffic, it will cost multiple seconds to run on an edge device. The device we use is Raspberry Pi, so that's have very, very limited computing power. Detecting the road surface condition and try to classify the condition into, for example, dry condition, wet condition, snow covered, partial snow covered, etc. So this is something very important for this particular project. We also need to detect vehicles. So we know how many vehicles going by, the sensor location, and what's the travel time. So this actually is the flow chart showing the algorithm. So given the time constraint, I will not go into the details of this. So basically the idea is we have a trigger algorithm that's very simple. If we found there's a vehicle getting into the scene, we'll trigger the AI algorithm to process, identify the vehicle, and classify the vehicle. So before we do actually the road surface condition detection, we have to know where is the road. So we actually invented several very creative algorithms try to take this function handled. So we have the optical flow approach combined with the motion vector and try to use the DB scan algorithm to identify the roadway section. So this slide shows actually two roadway examples. So the left column shows one roadway and the right shows another. This algorithm actually worked pretty well, so we don't need to be manually interacting with the system. You set up the system, so after there are multiple vehicles goes by the scene, we can automatically identify the road surface portion. So this particular algorithm is now being installed. So there are still other considerations that the Norwegian folks need to figure out. For example, how to comply the data privacy requirement. So they're still doing the testing and it's going to do the installation. So we don't have actually the data from Norway roadway yet. So to train our model, we collect a lot of data from the Washington State DOT's video cameras. So here shows some examples of those cameras. And the Star Lab has 2 fiber connections to the Washington State DOT Traffic Control Center. So we basically can access all the live video inputs from the WashDOT system. So here actually shows some examples of where the cameras are. And those are the places we gather video images with different kind of surface conditions. So the algorithm that we developed and tested are promising. So here shows the dry pavement also classified as dry is 97.5% accurate. For the snow detection, almost 98%. Partial snow, 90%. The rainy condition is tricky because rainy condition, the partial snow, there's not a clear border. So this is actually gets 85% accuracy. And the other category this confused the most is actually the partial snow category. So I consider this is kind of normal. So for the vehicle classification, we run a background subtraction, try to identify the blobs, and then use the deep learning algorithm to look into the blob to see if this is actually a vehicle. If yes, what kind of vehicle? So by doing so, we can significantly reduce the computing burden on the edge device. So this slide shows our traffic volume detection and the vehicle classification result. So you see the vehicle classification is also satisfactory. So we get pretty much 90% accuracy for different kinds of vehicles. Truck is a little bit tricky because the truck is long and sometimes may be having like the trailers in different color, etc. So this is 87%. There's still room to improve. For the model we developed using the Washington data, we use the transfer learning and try to train the model to adapt better to the Norwegian situation. And the data we used is the mile TCD dataset. So that's about the first example. So I want to just briefly mention our second example, which is the edge computing for curb space management. So we are doing this experiment right now in the city of Bellevue. Bellevue has this curbside management pilot project. The Star Lab and some commercial companies, they're testing the solution. There are two actually test locations. Location number one is actually a curbside space, very heavily used with different kind of vehicles like delivery trucks, passenger cars. And test location two is actually a kind of curbside area, normally with a lot of passenger car parked there. So you see this is a snapshot of curbside two. So our sensor installed, we have each side with one sensor. We've been collecting data. So far, we found actually our detection results is very promising. So in this particular curbside two, we pretty much get 100% accuracy, and the other side is close to about 95%. So this is the encouraging first step, and also shows the power of edge computing. With this edge computing device and technology, we only use T-Mobile's cell phone data package to communicate with the server. Majority of the work are actually done in the edge device. So another application example I want to show to everyone today is the edge computing for collision warning. So this is actually a research project funded by Federal Transit Administration. So we are partnered with Pierce Transit for the experiment. This project's PI, Dr. Jerry Lutin, he is also on today's webinar. He's listening, so he's actually very familiar with what we have been doing. He's actually the overall designer for the whole thing. We plan to install our edge computing device on 4 Pierce Transit buses. And the purpose for our system is really to evaluate DCS companies' past LiDAR system. So this is actually the LiDAR system installed in front of the bus. So we want to collect data to see how many warning messages generated by the DCS system, and are they actually true? So we want to give the performance measures like false positives, false negatives, this kind of information for the transit agencies to decide what to do with such advanced collision warning system. So our edge computing device installed on the buses and try to collect the near crash data. Maybe you wonder why near crash data. So this actually shows the relationship of the near crash or near miss to like the real crashes, like injury or fatal crashes. So there are certain relationships. So you may be observing very few like real crashes, but there are a lot of missed crashes. And then the missed crash data could also give you very good information about how you can improve the safety condition on the roadway or at the intersection, or how this may be used to train the drivers to improve their performance. Again, I will not go to the details of this flow chart. This is actually provided on the slides just in case somebody may be interested and want to take a close look. So our system basically collect information and process using our edge computing algorithms to see if there's a near crash event. If there is, we send a trigger. And the DCS system, the past system, also generate the same thing. If they see based on their LiDAR detection, there is a near crash event, they also send a trigger. And based on the trigger, we record a video so we can verify to see if there's a true event. If there's not, this is likely to be a false alarm. On another side, there may be a true event, maybe both systems missed, right? So in this case, we look at the G-force data, if the G-force data showing the driver has a sudden brake or sudden direction change, this may be corresponding to a potential near crash event the driver tried to avoid. So we also record video. So this may be used for identifying how many false negative events that the system has. So this is actually the system, like we use the existing dash camera on the buses facing the front. And this is our device. And we also need the power, try to support the device on the transit vehicle. Basically, we have a lot of new technologies applied in this particular application. So for the tools for deep learning on Jetson, we train the tools using TensorFlow and the TensorRT for neural network optimization. We actually have a lot of innovative parts for the entire algorithm design. So modeling and the bounding box generated by the object detection methods to estimate the time to collision and the relative motion. That's a very important innovation. So if you're interested in the details, you could look at our paper. We have a paper written for introducing the entire algorithm. There are a bunch of other things. I will not go over them in details. So this is how the system looked like. This is actually a cabinet inside the bus. And this is the PS Transit Bus 233. This is our device. We actually hooked into the power supply and the connections, video signal, and the communication lines, and then put into the cabinet. So it's still on the bus. When the bus drives by, we can collect information and process the data. So now let me show you a video. That's the demonstration video Raymond put together. Raymond is the key researcher for this particular project. I think this file is relatively big. I guess it may not be loading properly. Let me, okay. It doesn't have sound, so just you see how the system performs. So this system used NVIDIA Jetson TX2. So it's about $500 each device. And which can use just whatever camera face front. So we have just a regular USB camera we use for testing on our own vehicles. In the collaboration with the Pierce Transit, we are using their existing camera. So this is actually the test on Raymond's own vehicle. So anyway, such a system is relatively cheap and easy to deploy. And it generates really a lot of very meaningful information for the drivers and the agency to consider. This slide shows the data collected in October 2020. So the first row of the images showing the pedestrian near crash events, so where they happened. And the second row, the blue dots showing the vehicle warning message of 3 buses. So you see actually the location of them. You can actually zoom into the details to see exactly where you see more such events and whether we can take some solution to fix the problem to reduce this kind of near crash events. So that's pretty much all I have for today. So the key message to everyone is we are facing a lot of challenges in transportation engineering from the mobility side and also from the safety side. By using innovative technologies, particularly the edge computing technology and using the connected vehicle system, we can possibly address a lot of these challenges in a relatively cost-effective way. So with that, I want to say thank you everyone for your attention. And if you have any questions, I will be very happy to answer your questions.
Okay, thank you very much, Professor Wang. And as Professor Wang said, please feel free to type in your questions now in the Q&A box at the bottom of the screen, and I'll read them out loud to our presenter. I do have a question for you just to kick things off. So this work on near crash events is super interesting. What's next for this research, and are you working directly with any agencies?
We actually, today I showed 2 different systems. One is the vehicle-based, is the near crash event detection. Another is infrastructure-based. That's like the master sensor technology for highway monitoring and like a curb space management, intersection control, etc. So we are working with agencies like the first one we've been working with Norwegian Public Road Administration, Washington State DOT, the city of Bellevue. And the vehicle-based technology actually was supported by Federal Transit Administration. We have been working with Pierce Transit, Dr. Lutin, and Virginia Tech, and several other vendors of the technology like DCS, try to see if we can apply this technology to make our transit vehicles safer.
And where are you in the process? Like, how far along are you in let's say agency adoption?
Oh, I think they are, in my opinion, both technology are ready or very close to get ready. I'd say we see most of the problems being fixed. If you look at our mass sensor, this is designed for operating temperature from -40 degrees to 158 degrees. So it's quite a large range. Otherwise, it won't survive in Norway, which could have the cold winter, the temperature as low as -40 degrees Fahrenheit. And it's designed and made like a professional makers. We actually try to satisfy all kinds of industry standard. So I have to say the mass sensor is ready for being adopted and used. So we test different kind of functions, but that's not the only functions the device could support. So this device is actually just an edge computing device. If you guys find this could be used for another purpose, for example, you see this may be used for like a school district crossing, you have an algorithm. You can develop that and put the algorithm on the platform, hang this up, and this will be, doing its job, collecting data, sending warning messages, or collecting input from the users. For the Jetson device-based algorithm, we are testing. So I think this one, if it works fine for our testing, it could provide off the market cost-effective solution for the transit agency or even just the passenger car owners to gather data and collect some useful information during their journey. So I have to say, both technologies are getting to the stage and ready to be used. There may be still problems before it gets 100% mature, but I think they could be applied now.
Okay, so similarly, and this is a very large general question, but how do you think the COVID-19 pandemic and the ensuing world of remote work has affected the rate of the technological advances you've been speaking about today?
The COVID-19 certainly affects, our teamwork. It has to be remote. It cannot be really everybody sit by the table and discuss. But we have been trying to move this forward as much as possible. But there's one project now currently being delayed, and we ask for 6 months no cost extensions to use our mass sensor at signalized intersections, try to communicate with user cell phone about the timing plan. So that one we're supposed to be in the field test, but because of the COVID-19, this was delayed. But we're still considering when we want to start this. We don't want to make this delay for too long.
Yinhai, this is Khan. I have a quick question on the LiDAR project for the bus. Maybe I missed that slide. So where do you place the LiDAR? It's on the, where in the bus?
Oh, that LiDAR is not our LiDAR system. It's a company's LiDAR system. So they installed a LiDAR in front of the bus. The bus normally may have a bicycle rack, right? They install that under the rack and cover a certain angle in front of the bus. So that's for like a near crash event detection and warning. So our Jetson device is actually also installed on the bus, try to collect evidence to evaluate that particular system.
So with the LiDAR being outside the bus, don't they have a problem of like a mud or other things like, blocking the LiDAR? I mean, because if you're traveling on a rainy day, if there's a lot of, mud and things like that, you might not get the same accuracy from the LiDAR. No? I mean, or isn't that a problem? I mean, I'm not a LiDAR expert, but I was just with the camera, we always see that problem. I mean, even the traffic cameras, now they have wipers, and keeping them clean, and it's a problem. So when like a vehicle traveling on the road, how do they do that? Do you have like a wiper, or I haven't seen that.
I think certainly you raised great question, Ken. I think keep the sensors clean is quite important for autonomous vehicles. This LiDAR system, as I said, is not our research product. We'll be very happy to link you to the right person that developed the product. So you could directly discuss some technical details with them.
Because the camera can be inside, like a dashboard, whatever. So with that, there's no problem. So.
But the LiDAR has to be outside, right? So you see like an autonomous vehicle, they use the LiDAR and install the LiDAR on top of the vehicle, the spinning around, try to scan the surrounding environment. And some design of the autonomous vehicle may have multiple LiDARs, like the top one, and each side they have another one. So Elon Musk criticized this LiDAR-based idea because he considered LiDAR is too expensive, and he prefers other technologies, particularly video. But video has its own problem too. When in the night, the light is not sufficient.
And also,
the video may not be able to see.
With video, the depth, getting the depth, the perspective, it's not that easy. With LiDAR, that's, kind of given. So that's.
So we have a couple of questions that have just come in from participants. First from Shi. Can these edge devices, so you talked about these edge devices transmitting information to like a TMC, but can these edge devices actually make the decisions using detected traffic data?
Yeah, actually, we don't have to communicate with, let's say, TMC. Let's say an application now we submitted to the Everyday Count program, like the state program in Washington, was trying to work with the city of Linwood and city of Bellevue, hang up the device at the dangerous roadway segment. In the winter, they may be very slippery and with a big slope. In that situation, if we detect a danger on the road surface, we could just send out a message to the users. But before the traffic operators, the cities trust this, they may want to see what kind of message you want to send, and what is the situation. So we could just send the snapshot of the road surface and our conclusion, our recommended message, all to the city traffic control room. They can review, and if they agree, this will go out. But once they trust the system, I think the system may also be located in a very rural location with a dangerous road segment, but has no communication. The device could be just working all by itself, detecting traffic, detecting road surface condition, the weather, humidity, visibility, and communicate with the users directly.
Okay. So this question is, can you elaborate a bit more on the detection accuracy, for example, in terms of different traffic conditions, especially for the vehicle-based device?
I think this one, we actually tested with the training images, we can estimate, right? So we estimate that, so that detection accuracy is, I think, at about like 80 to 85 to 95% range. This kind of AI algorithm all depends on how well you train the model. So we use a limited amount of images that we can gather and train the model to, I think, a pretty good accuracy level. We're still keep optimizing it, make it more accurate. So this is something, I think, an ongoing process, but I can tell you at this point, the accuracy is pretty good compared to a lot of other research. I think we're on the high accuracy end. In the city of Bellevue's curb space management project, as we said, we just had a project meeting recently, go over the accuracy. We found actually the site 2 accuracy is 100%. And site 1 is 94%. There are large vehicle occlusion problem. If you work on video detection, occlusion is a killer. The big truck stopped by, close to the camera, and the camera does not see the vehicle at all, or maybe only see the vehicle parking behind the truck, very small portion. So that's normally where's the error from. Other than that, I think the current algorithm we implemented is effective and also operable in the edge device without causing trouble in the edge side.
Okay, so we have one last, more of a statement than a question, but Jerome Luton is watching right now, and he says, since you're appearing on the East Coast, he wanted to just attend your talk and wishing you a happy Thanksgiving. So with that, I think there's no better opportunity to close. Just a quick note before we wrap up. If you enjoyed this webinar, definitely follow C2 Smart on Twitter, join the LinkedIn group that we have, join our mailing list. Our next webinar is going to be on December 8th on the topic of autonomous driving and energy efficient traffic smoothing with Professor Benedetto Piccoli of Rutgers. So staying on the topic of autonomous vehicles. Professor Wang, thank you so much for coming out to speak with us today. We hope to get you back here on the C2 Smart webinar series sometime soon.
Thank you,
Thank you,
Yinhai.
John.
That was a great talk. Thank you. And again, we hope to see you in person very soon.
Thanks, Ken. Thanks, everyone, for joining my webinar. I really appreciate your time. If you have any feedback, you see my contact information is on the first slide, so you could communicate with me directly. Thanks a lot, and happy holidays to everyone.
See you too. Bye-bye.
Thanks a lot.
Goodbye.